Welcome to The Deep Dive. Today, we're taking a magnifying glass to something that is, well, it's hiding right in plain sight.
Oh, absolutely everywhere.
Right. We're going to explore those massive, um, seemingly featureless industrial buildings that you probably drive past on the highway every single day.
Yeah, the giant gray boxes.
Exactly, the giant gray boxes. We're talking about the hidden logic behind industrial warehouse design and logistics. And we've got an incredibly dense source text guiding our conversation today. It's an excerpted guide titled The Industrial Machine, a guide to warehouse design logistics.
It's a great title.
It really is. And to jump right in, I mean, we rarely think about these industrial structures, right? They aren't glamorous at all.
No sweeping architectural curves.
Right, no aesthetic flourishes, but if you're in the industry or if you're studying the underlying mechanics of global trade, you know that these are the invisible engines powering our daily lives. Every single thing you own.
Literally everything.
Everything.
Yeah.
From the device you're using right now to listen to this, to the furniture in your living room, it all spent time in one of these massive structures.
Right.
And the core metaphor from our source text completely shifts how we should view them. The text argues that we need to stop thinking of these structures as mere buildings. We have to start evaluating them as a logistics machine, built exclusively for trucks and goods.
And when you make that mental shift, the entire landscape of industrial real estate suddenly snaps right into focus.
Yeah.
What's fascinating here is that when you look at an industrial space through the lens of a logistics machine, you realize that every single design feature exists strictly for operational efficiency.
Right.
We're talking specifically about loading, storage, and movement.
Mm-hmm.
These buildings are not designed for human comfort in the way a residential or, a commercial high-rise is.
Not at all.
They are giant static engines designed to process the physical economy.
A giant static engine. That's just the perfect framing. And to understand how this engine works, we're going to break down 7 crucial design features today.
Sounds good.
We're going to uncover how this machine actually operates, piece by piece, relying on the exam logic provided in our source material. Because this isn't just about what a building looks like.
No, it's about the why.
Right, it's about giving you the cheat codes to understand why it was built that way. We'll look at the specific physics of how things get in, how they move around, how they're stored, and how they are pushed back out into the world.
Let's do it.
Okay, let's unpack this. I want to start with the gateway of the machine. The loading dock.
The loading dock.
Yeah. Our source establishes the loading dock as a raised platform where trucks load or unload goods into the building. But, anyone who has spent 5 minutes looking at supply chain logistics knows it's not just a ledge.
Right.
It is a highly engineered transition point.
It is a deceptively simple piece of engineering that solves a massive physical problem. The source emphasizes why this matters so much. The loading dock creates a seamless horizontal plane.
A horizontal plane.
Exactly. It allows forklifts to move goods directly between the truck and the warehouse floor. If we connect this to the bigger picture, think about the physics of movement. Every time you have to lift something heavy up
Or lower it down.
or lower it down, you are fighting gravity. You're expending extra kinetic energy, burning fuel, wearing out machinery, and more importantly, in the world of logistics, you are bleeding time.
And in logistics, bleeding time is bleeding capital.
100%.
By raising the floor of the building to the exact height of the bed of a standard trailer, which is usually right around 48 inches, I think you eliminate that vertical movement entirely. You turn the transition from the vehicle to the building into a smooth, horizontal glide.
Seamless.
But the text also implies that achieving this perfect horizontal plane isn't just about pouring concrete to the right height, is it? You have dynamic loads to consider.
Oh, massive dynamic loads.
Right. When a forklift carrying, say, 4,000 pounds of flat pack furniture rolls over the threshold from the concrete dock into a steel truck trailer, that is a massive transfer of kinetic energy.
Exactly. And that's where the nuance of the machine comes in. The dock isn't just a static shelf.
Right.
It involves dock levelers.
Right. The levelers.
Usually pneumatic or hydraulic plates that bridge the gap between the building and the truck bed. Because that truck bed constantly flexes as the weight inside the trailer changes.
Just moving up and down.
The truck literally sinks on its suspension as the heavy forklift drives in, and then it rises as it drives out. The loading dock has to actively manage that physical reality to maintain that horizontal plane.
That makes sense. And the source gives a great real-world example to illustrate this continuous motion. Imagine a regional distribution center receiving a massive shipment of that furniture. The truck backs up and docks perfectly flush. Because that horizontal plane is established and actively maintained by the dock levelers, a forklift can roll right out of the building, drive directly into the back of the trailer, secure the heavy pallets, and reverse smoothly.
No ramp required.
No crane needed, no ramps to navigate. Those pallets go straight into the warehouse for put away. It is relentless, continuous motion.
And that continuous motion is the absolute lifeblood of the facility. But that brings us to the critical vulnerability of the system, which the text highlights as a primary exam concept.
Okay.
Let's talk about the bottleneck effect.
Okay.
If there are too few docks built into the side of the machine relative to the cubic volume of the warehouse, what happens?
You get a yard jam.
Exactly.
The trucks just start lining up outside.
Precisely. The deliveries grind to a complete halt. It does not matter if the inside of your warehouse is the most efficient, hyper-automated storage facility on the planet. If the gateway is choked, the entire machine fails. Drivers hit their hours of service limits while sitting in the yard, demurrage charges rack up, and the supply chain fractures.
It's a disaster.
It is. This directly connects to the exam logic our source emphasizes. More docks simply equal a better setup for high-volume distribution centers.
Volume is key.
If the goal is high volume, you need a high number of simultaneous entry and exit points. A standard ratio developers look at is one dock door for every 10,000 square feet of warehouse space.
Wow, okay.
So if you see a 1,000,000 square foot facility, you should expect to see around 100 dock doors to prevent that bottleneck.
It's a pure capacity calculation at the gateway. But our source also pivots to a completely different type of entry point, which contrasts perfectly with the raised loading dock.
Right.
Let's look at grade level doors. Grade level simply meaning they are cut right there at the ground floor.
Ground level.
Right. These are massive roll-up doors that allow vans, or even smaller box trucks, to drive directly into the building itself. You aren't bridging a gap between a truck bed and a raised floor.
No, you're opening a physical hole in the wall at street level.
Exactly. And the source makes it very clear when and why you would utilize this alternative design.
Grade level doors are utilized primarily when heavy-duty forklifts are not the primary mechanism for the unloading process.
Okay.
The text provides a contrasting example to the massive furniture delivery. Imagine a smaller, local manufacturing company or a specialized fabricator. They aren't receiving 40,000-pound loads on tractor trailers.
Right. They don't need that scale.
Exactly. They're receiving smaller, specialized parts, maybe custom tooling or raw materials, arriving in standard delivery vans or sprinter vans.
And in that scenario, a raised dock is actually a hindrance, isn't it?
It totally is.
If a standard delivery van backs up to a 48-inch high loading dock, the back doors of the van are sitting way below the concrete floor.
You can't reach it.
You can't unload it. So instead, the delivery van just rolls right up to the building. They roll up that grade level door, and the van drives inside.
Or parks right at the threshold.
Right. The workers can manually unload the boxes directly into the workspace. It requires zero heavy machinery to make the transition.
And the exam logic presented in our source for this is crucial for anyone evaluating industrial spaces. Grade-level doors are common in smaller industrial buildings.
Often called flex space, right?
Yes, flex space or light industrial. They represent a completely different scale of operations. It contrasts perfectly with the high-volume loading docks.
So a massive regional distribution center thrives on dozens of raised loading docks to handle 18-wheelers.
Yep.
While a small local fabrication shop thrives on a couple of grade-level doors to handle local courier bins. Both are valid designs, but they serve entirely different types of logistics machines.
Perfectly said.
Okay, so we've established the gateways, the raised docks, and the grade doors. But how do the massive trucks actually navigate to those loading docks in the first place?
That's the real trick.
Right, because if you've got 100 dock doors, you have a massive orchestration problem outside the building. And that leads us to the next critical feature.
The shipping aprons and turning radiuses.
Yes. The source introduces this concept of the shipping apron. It describes it as the massive concrete area immediately outside the loading docks. If you want to visualize it, think of it as the ultimate truck parking and maneuvering zone.
It is the operational stage where all the external choreography happens. And to understand why the shipping apron is so vital, you have to look at the specific vehicle it is designed to accommodate.
The 53-foot trailer.
The 53-foot trailer attached to a standard cab. The source lays out the specific physical movements required for one of these massive vehicles to interact with a loading dock. It is not like parallel parking a sedan.
I would hope not.
The driver has to execute a really complex maneuver. They have to back the trailer perfectly square into a narrow 9-foot wide dock door.
That's a tight squeeze.
Very tight.
Yeah.
To do that, they have to pull forward, swing wide, align the cab, straighten the 53-foot trailer out completely, and then carefully reverse it.
And without a massive, unobstructed shipping apron, that alignment is geometrically impossible. If the apron is too shallow, say only 60 feet deep, the truck simply cannot get straight before the rear of the trailer hits the dock.
Right.
And if the trailer goes in at an angle, the dock seals won't engage. The pneumatic leveler we talked about won't seat properly on the truck bed, and the horizontal plane is completely compromised.
It breaks the machine.
The forklift can't safely cross the threshold. The machine breaks down before the goods even touch the building. Industry standard usually dictates an apron depth of at least 130 to 185 feet.
Depending on the yard configuration, yeah. But here is a hidden detail from the source that serves as a vital exam tip.
Okay.
The shipping apron must be made of reinforced concrete.
Not asphalt.
Right. Why is that specific material so vital? Why can't a developer just lay down standard asphalt to save a massive amount of capital on the bill?
It comes down to basic physics and the relentless, punishing nature of the logistics machine. The source points out that an empty tractor trailer is heavy, but a fully loaded one can weigh up to 80,000 pounds.
Massive weight.
That exerts an immense, concentrated amount of pressure onto the ground, specifically right where the rear axles pivot and turn. When a truck is backing into a dock, those dual tires are scrubbing against the surface under all that weight.
Scrubbing hard. And if you were to use standard materials, like the asphalt used for a typical retail parking lot, it would fail catastrophically.
Because it's too soft.
Asphalt is technically a highly viscous liquid. It shifts and moves under heat and pressure. The repeated pressure of heavy tires turning in the exact same spots day after day, year after year, especially in high summer temperatures.
Oh man, summer heat on asphalt.
It would tear standard asphalt to shreds. It would create massive ruts, divots, and potholes.
And once you have massive ruts right in front of the dock, what happens? The truck trailer isn't sitting level anymore. The horizontal plane is destroyed.
Exactly. Reinforced concrete, poured thick, usually 8 to 10 inches minimum, and laced with a dense lattice of steel rebar, is the only material capable of withstanding the dynamic loads and the twisting shear forces of this environment.
It's fascinating.
It's a prime example of how the function dictates the very materials of the machine. The exam logic here is clear. If you are evaluating an industrial site and the apron is asphalt, you are looking at an impending capital expenditure nightmare.
That makes perfect sense. The machine has to be durable enough to survive its own violent operations. Now, intrinsically linked to that massive apron is another vital spatial concept our source covers, the truck turning radius.
Right.
This is defined simply as the amount of space big trucks need to turn around safely. But again, let's go deeper than just big trucks need big spaces.
This is where scale becomes the defining factor of industrial real estate. Logistics architects use software to conduct what is called swept path analysis.
So swept path analysis.
Yes. They literally map the exact turning vectors of multi-axle vehicles to ensure they can navigate the property without colliding with the building, fencing, or other parked trailers.
It's all simulated beforehand.
Exactly. The source draws a contrast to help visualize this scale. A small delivery van, the kind that might use those grade-level doors, can zip around a tight parking lot with ease. It can make sharp turns and reverse in tight quarters.
Sure.
But an 18-wheeler, a tractor pulling a 53-foot trailer, demands a massive, sweeping turning radius.
And the source is adamant on this point. Distribution centers absolutely must have these large turning areas. The entire goal of this facility is continuous, uninterrupted throughput.
Continuous throughput.
If a truck has to perform a 10-point turn just to get out of the lot, or worse, if it sideswipes a structural column or another parked truck while trying to navigate a tight corner, the flow stops. You have an accident report, insurance claims, blocked docks, and lost time.
It's a disaster for velocity.
Right. Therefore, the exam logic here is unbreakable. Large distribution centers inherently require a large truck turning radius.
Which means the geometry of the truck dictates the geometry of the real estate.
That's a great way to put it.
You cannot build a massive, high-volume facility on a cramped, oddly shaped plot of land, no matter how cheap that land is to acquire. If the swept path analysis shows the trucks can't turn comfortably, the site is functionally obsolete before you even pour the foundation.
The building is entirely a servant to the vehicle.
Exactly.
Okay, so we've solved the problem of getting the truck onto the property, turning it around safely, and perfectly docking it using those reinforced concrete aprons to maintain that crucial horizontal plane. But once those bay doors open and the goods actually move inside, you're faced with a completely different mathematical challenge.
The interior.
The geometry of the interior space. Let's maximize the inner void. We are talking about ceiling height and column spacing.
This is where the true optimization of the machine happens.
I want to focus on ceiling height first, which the source and the industry refer to precisely as clear height. It's an important distinction. Clear height is not the distance to the roof deck.
Right.
It is defined precisely as the vertical space from the concrete floor to the absolute lowest ceiling obstruction. That could be an ESFR sprinkler head, a massive lighting fixture, or a steel roof joist.
And understanding why clear height matters is a total game changer for understanding warehouse efficiency. It introduces the math of vertical optimization.
Vertical optimization.
When a developer looks at a piece of land, they see two-dimensional square footage. But a warehouse does not operate in 2 dimensions. It operates in 3.
It's all about volume.
It is entirely about cubic volume. Higher ceilings allow for vertical storage, which means you are multiplying the value of the land beneath the building. In markets where land acquisition costs are astronomical, think Los Angeles, northern New Jersey, or outside London, you can't just build wider.
You have to build higher.
Exactly.
Yeah. Our source gives a very straightforward comparison. Let's walk through the math on this. We have warehouse A and warehouse B. They both take up the exact same amount of land, let's say 100,000 square feet. They have the identical footprint.
Okay.
But warehouse A is a legacy building constructed in the 1980s. It only has a 20-foot clear height. Because the ceiling is relatively low, and you have to account for the space needed for the sprinkler systems to operate effectively over the goods, you can realistically only rack pallets 3 levels high.
Right. Now look at warehouse B. It has the exact same 100,000 square foot footprint on the ground, but it is a modern facility with a 40-foot clear height.
It's double the height.
That massive increase allows the operator to install towering, multiple stacked pallet racks. You can stack pallets 5, 6, or even 7 levels high. And you're using specialized wire-guided forklifts that operate in very narrow aisles to reach them.
So the conclusion is staggering. Warehouse B might hold double the amount of inventory, double the pallet positions than Warehouse A, despite taking up the exact same amount of physical land.
It's a massive multiplier effect on throughput capacity.
And the source drives home the exam logic here. Because of this massive efficiency gain, modern warehouses usually feature a 36 to 40-foot clear height as the standard. Anything less is considered functionally obsolete for major regional distribution.
But here's where we have to apply some critical thinking to the text.
Okay, let's hear.
The source pushes for 40-foot clear heights, which makes sense for storage density. But structurally, pushing a roof up to 40 feet creates massive engineering tension.
How so?
Well, you have incredibly high walls acting as massive sails, capturing wind shear. You have to support an immense roof structure that has to bear the weight of snow loads in northern climates.
Right, that vertical space isn't actually free real estate. The developer has to spend significantly more capital on heavier steel, stronger tilt-up concrete panels, and more robust foundation footings to support that 40-foot box.
Yes, but the exam logic holds because the operator is willing to pay a premium lease rate for that cubic volume. The cost of the heavy steel is offset by the storage density.
Exactly. But while we are looking up at that glorious, unobstructed 40-foot ceiling, we eventually have to look back down at the floor. Because holding up that massive roof requires structural support.
You can't avoid gravity.
You cannot. And that brings us to the next critical concept, column spacing. This is the distance between the vertical structural steel columns holding up the roof grid.
And as our source explicitly states, if vertical space is the hero of the warehouse, columns are the absolute villains.
The villains?
Columns are the enemy of speed. Why? Because columns represent permanent, immovable obstacles on the warehouse floor. They block forklifts. They dictate exactly where you can and cannot place your massive storage rack.
They dictate the flow.
They force the logistics machine to work around them, rather than the other way around. They create an obstacle course.
Let's go back to our comparison. In Warehouse A, the older design, the engineering might have required columns to be placed every 25 feet. Imagine trying to design an efficient racking layout or drive a forklift through a grid where there is a massive steel pillar every 25 feet in every direction.
It's a nightmare.
The forklift driver is constantly steering around them, slowing down to navigate blind corners, meticulously avoiding collisions. Every column represents a dead zone where a pallet cannot be stored. It's a frustrating, inefficient maze.
Now contrast that with Warehouse B. Modern engineering and stronger steel allow for columns to be spaced every 50 to 55 feet.
That's a huge difference.
That extra 25 feet of space between supports changes the entire geometry of the floor plan. Instead of a tight maze, you have massive, wide-open lanes. The forklifts can move at top speed. You can configure your storage racks in long, uninterrupted rows, maximizing every square inch of the floor.
So the conclusion from the source is crystal clear. Wide column spacing equals significantly better warehouse functionality. Fewer columns mean more freedom, more speed, and a highly optimized storage design.
But again, let's probe that logic. Just like pushing the roof to 40 feet, widening the column spacing to 50 or 60 feet requires incredibly robust, expensive, long-span steel joists to hold up the roof over that wide gap.
It's another massive capital investment.
It is. But the text argues that it is necessary to minimize friction inside the machine. Think about it. If a forklift can shave 3 seconds off every single pallet pick because they don't have to navigate around a tight column, and they perform 1,000 picks a day.
That wide column spacing pays for itself very quickly.
Exactly. In labor savings and throughput velocity.
It all comes back to throughput velocity. Now, everything we've talked about so far, the docks, the reinforced aprons, the vertical cubic storage, the wide column grids, assumes the traditional role of a warehouse. You bring goods in, you store them on a rack for a while, and eventually, a day, a week, or a month later, you ship them out.
Right, that's the standard model.
But our source introduces a final design concept that completely upends that traditional model. It's a concept called cross-docking.
Wow.
Here's where it gets really interesting. And this completely flips the script on what a warehouse fundamentally is. It is all about bypassing storage entirely.
It is a radical shift in logistics philosophy. The source defines cross-docking as a specific facility design where goods move directly from the inbound incoming trucks to the outbound outgoing trucks with minimal to absolutely no storage involved in the middle.
Hence the name.
Think about the word itself, cross-docking. You are literally crossing the dock. You take a pallet out of a truck on the north side of the building, you move it straight across the floor, and you load it directly into a different truck waiting on the south side of the building.
And our source illustrates this with a perfect, everyday example, a courier distribution center. Think about the e-commerce packages you order online. When a massive 53-foot truck full of assorted, unsorted packages arrives at a courier facility, those packages are not put on a shelf to sit in inventory.
They don't have time for that.
Right. They are unloaded, they hit a series of fast-moving, automated sortation conveyor belts, they are immediately scanned and sorted by zip code or specific delivery route, and they are loaded straight onto the smaller local delivery vans waiting on the exact opposite side of the building. The goods never stop moving.
And that is the key takeaway for the exam logic. The cross-docking design fundamentally prioritizes speed over capacity. It is not about how much cubic volume you can hold. It is entirely about how fast you can process the flow.
Speed is everything here.
The text is blunt. Cross-docking increases distribution speed exponentially. It accelerates the supply chain by entirely eliminating the two most time-consuming and labor-intensive steps in traditional warehousing. Put away, which is driving the pallet into the racks, and picking, which is retrieving the pallet from the racks later.
In a pure cross-docking facility, the building isn't a storage box at all. It is merely a valve. It's a covered sorting mechanism designed to protect the goods from the weather while they are in constant motion between vehicles.
Exactly.
Because of this, cross-dock facilities look very different architecturally. They're often very long and very narrow. They don't need the massive 40-foot clear heights because they aren't racking pallets vertically. Instead, they maximize the number of dock doors on both sides of a long, narrow rectangle to minimize the travel distance across the floor.
It's mesmerizing when you understand the mechanics of it. It really highlights how dynamic and highly specialized these supposedly boring buildings actually are.
Yeah.
You aren't just building a gray box. You are building a specific tool for a specific type of supply chain velocity.
All right, we've covered a tremendous amount of ground here. We've looked at the physics of the loading docks, The vital necessity of grade-level doors for smaller operations, the vast reinforced concrete shipping aprons, the swept path geometry of turning radiuses, the cubic math of towering clear heights, the operational freedom of wide column spacing, and the relentless velocity of cross-docking.
We really hit it all.
Now, our source text distills everything we've analyzed into a shockingly simple, elegant formula. If you want a cheat code to remember the core philosophy of industrial real estate design, just think of two words: trucks plus storage.
Truxismus plus storage. It is the unifying theory of the industrial machine. The source reiterates that these buildings are designed, funded, and built to optimize three specific pillars: truck movement, storage efficiency, and fast loading and unloading.
Yeah.
That is it. That is their entire reason for existing on the landscape.
So simple.
Therefore, from an exam perspective, or just from a practical investment perspective, anything that improves those three core pillars is usually the correct answer. The machine only cares about the flow of goods.
And to prove that point, the source actually provides a quick practice example, formatted like a real exam question. I want to put you, the listener, to the test right now. Think about the deep dive we just did. Think about the dynamic loads, the swept path analysis, the cubic volume. Here's the question directly from the text. Which feature is most important for a large distribution warehouse? Here are your options.
Pay attention.
Option A, decorative building facade. Option B, large truck turning radius. Option C, landscaping design. Option D, skylight windows. Take a second. Apply the unifying theory of the machine.
The answer, of course, is B, large truck turning radius. And the why behind that answer walks in everything we've covered today.
Tell us why.
The text explains that the fundamental reasoning is simple. Distribution centers depend entirely on truck logistics. A large turning radius directly facilitates the movement of those 53-foot trailers, ensuring the machine doesn't joke on its own physical constraints.
Exactly. And let's look at why the other options fail the test. Option A, a decorative building facade. The machine does not care what it looks like from the highway. A sleek glass entrance does not increase throughput velocity.
Not even a little.
Option C, landscaping design. Trees and elaborate bushes do not help a forklift load a pallet faster. In fact, they might obscure the line of sight for a driver backing into a dock. Option D, skylight windows. While nice for natural light and potentially lowering the electric bill slightly, they do not inherently improve cubic storage density or loading speed.
They're a bonus, not a requirement.
Right. Those aesthetic or minor operational choices are completely secondary to the machine's primary brutalist function. It all comes back to truck-X plus storage.
The exam question brilliantly exposes the difference between architectural vanity and industrial utility. You evaluate the building solely on its ability to process volume. If a feature doesn't move a truck faster or store a pallet higher, it is structurally irrelevant to the machine.
So what does this all mean for us? We've reached the end of our source material, but I think unpacking this text completely changes how you view the physical world around you.
No, without a doubt.
The next time you are driving down the interstate and you pass one of those sprawling million-square-foot white or gray boxes, you won't just see a boring building anymore. You will see the incredibly thick, reinforced concrete aprons absorbing the torsional weight of 1,000 turning trucks.
You'll see the horizontal plane.
Right. You will imagine the cavernous 40-foot clear heights inside, packed to the steel rafters with vertical inventory. You will envision the choreography of wire-guided forklifts darting smoothly between wide-spaced columns, or the relentless, pulsing, automated flow of a cross-docking operation. You aren't just looking at architecture, you are looking at the vital, beating organs of the global economy.
It truly is a hidden world of pure logistical physics. And before we wrap up, I want to leave you with one final thought to mull over.
Let's hear it.
It builds upon everything our source text laid out, specifically regarding that final concept we discussed, cross-docking. We talked extensively about how cross-docking pushes goods straight from an inbound truck to an outbound truck with zero storage. The goal there is pure, uninterrupted velocity.
Right.
It raises an incredible question for the future of industrial design. If the ultimate optimized goal of the industrial machine is to completely eliminate downtime and maximize throughput, will future distribution centers eventually eliminate the warehouse part entirely?
Wait, entirely?
Yeah. If cross-docking is the ultimate speed hack, could tomorrow's logistics hubs cease to be static buildings with walls and roofs at all? Could they just evolve into massive, highly automated enclosed highway intersections where autonomous trucks in constant, coordinated, algorithmic motion act as the only rolling storage we ever actually need?
A global logistics network where the inventory literally never stops moving. The truck is the warehouse. That is a wild paradigm-shifting image to end on. Thank you so much for joining us on this deep dive into the industrial machine. I hope you found it as fascinating as we did. Keep your eyes open, keep analyzing the hidden mechanics and the supply chains around you, and remember that even the most unassuming gray box on the side of the highway is a marvel of calculated, hyper-efficient design. Until next time.